Chapter 6 Quick Quiz. Number 1, it says in exercise 1 through 4, assume that scores on a bone mineral density test are normally distributed with a mean of 0 and a standard deviation of 1. So number 1, bone density. Sketch a graph showing the shape of the distribution of bone density test scores. And that should look something about like this. Standard normal curve. Number 2, find the score separating the lowest 9% from the highest 91%. So I'm going to draw another one, and I'm going to draw it right here. Let's see. And I want to find the lowest 9%. And I'm going to say it's right in here. 0.09. So what I'm actually looking for is the z-score. So I'm going to go to my calculator, menu, 5, 5, and 3. Area 0.09. And that gives me negative 1.34. So this z-score is negative 1.34. Excellent. Number 3. For a randomly selected subject, find the probability of a score greater than negative 2.93. Let's draw us another. I need to practice. We'll draw us another one here. See what I need to practice. All right, so find the probability of a score greater than negative 2.93. So I'm going to say that's over here somewhere. Z equals negative 2.93. And I want to find this area here. Okay. So I'm going to go to my calculator. I'll say menu, 5, 5, 2, and I'm going to put my lower bound is negative 2.93. My upper bound is positive infinity. And that gives me 0.9983. So this area here is 0.9983. Number 4, for a randomly selected subject, find the probability of a score between 0.87 and 1.78. So I'll just put number 4 right here. Number 4. And I am looking for, let's see, negative 0.87. So Z equals 0.87 to 1.78. Z equals 1.78. And I'm looking for the area in here. I'm looking for this area here. So I'm going to go to my calculator, menu, 5, 5, 2. Lower bound is going to be 0.87. Upper bound is going to be 1.78, and I get 0.1546. So 0.1546. And I got this number here over, this is positive, so it should have been over here. That's positive. Let me fix that. I don't know why I just drew it way over there. 1 would be right here, so 1.87 would be about right in there. Z equals 0.87. So I was actually only looking for this area in here, which is why it's so small. Remember, when you draw this, you have here in the middle, we'll say that's the middle. This is 0. These over here are positive. These over here are negative. Okay. Number 5, notation. Identify the values of mu and sigma for the standard normal distribution. Mu equals 0 and sigma equals 1. What do the sigma? That's A. B, mu sub x bar is the mean of the sample means. And it is always the mean. And sigma x bar is the standard deviation of the sample. Standard deviation of the population, well, actually, sample means. Or of all. Let's see, all. Six, diastolic blood pressure. Find the probability that a randomly selected woman has a normal diastolic blood pressure level, which is below 80 millimeters. Okay. Find the probability that a randomly selected woman has a normal, let's see here. Assume that women have a diastolic blood pressure that are normally distributed with a mean of 70.2 and a standard deviation of 11.2. So now we're going to find the probability that X is less than 80. All right. So we're going to go menu 552. Lower bound is going to be negative infinity. Upper bound is going to be 80. Standard deviation is going to be 70.2. And the mean is going to be, the mean is 70.2. The standard deviation is 11.2. And it's going to be 0.8092. Number 7, diastolic blood pressure. Find the probability that a randomly selected woman has a diastolic blood pressure between 60 millimeters and 80 millimeters. Okay, so the probability that 60 is less than X is less than 80. All right. Menu 552, 60 for the lower, 80 for the upper, 70.2 for the mean, and 11.2 for the standard deviation. And we get 0.62799 or 0.628. 0.6280. Number 8, diastolic blood pressure. Find the 90th percentile. Okay, when we're finding the 90th percentile, let's draw a little thing here. And we'll put some, okay, this is 0.90, and this over here is 0.10, and we're just finding that Z. Okay, so let's go in here, menu 553, 0.9, and we get 1.28. So Z equals 1.28. Oh, hold a second. We got to use the 70.2 and whatnot. We can do this and then convert it over, but let's do it the easy way. Menu 553, 0.90. Our mean is 70.2. Our standard deviation is 11.2. And we get 84.55. So we'll just say 84.6. All right. Number 9. Diastolic blood pressure. If 16 women are randomly selected, find the probability that the mean of their diastolic blood pressure levels is less than 75. So now we have N equals 16. So we're doing the sample, we're doing this right here. All right. So the mean of X bar is going to be 70.2. The standard deviation of X bar is going to be 11.2 divided by the square root of 16. So 11.2 divided by the square root of 16, and we get 2.8. All right, now let's see. Menu 552. Lower bound is negative infinity. Upper bound is 75. The mean is 70.2, and the standard deviation, I know I calculated it over here, but in the lesson, I always did 11.2 divided by the square root of 16. And it's 0.9568. So the probability that X bar is less than 75 equals 0.9568. Number 10, the accompanying normal quartile plot was constructed from the diastolic blood pressure levels of a sample of women. What does this graph suggest about the diastolic blood pressure levels of women? it suggests that diastolic blood pressure levels of women are normally distributed. Almost all of them are touching the line. All right, good deal. So that's the quick quiz. Now let's do the review exercises. And those are on page 292. Number 1, it says bone density test. A bone mineral density test is used to identify a bone disease. The result of a bone density test is commonly measured as a Z-score, and the population of Z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So A, for a randomly selected subject, find the probability of a bone density test score less than 1.54. So the probability that Z is less than 1.54. Menu 552, negative infinity 1.54, and then we just press enter and we got 0.9382. B, for a randomly selected subject, find the probability of a bone density test score greater than negative 1.54. Probability that Z is greater than negative 1.54. So let's go over here. Menu 552, yes. Negative 1.54, positive infinity. And we get 0.9382. I wonder why that happened. Why did we get the same that? Remember, the standard normal curve is symmetric, right? It is symmetric. Even though Mr. Carbonell can't draw it symmetric, it is symmetric. Okay, and here is 0. So if you got something 1.54, 0 equals 1.54 over here, you've got a negative 1.54 over there. If this is 90%, or this is 0.9382, then this area over here would be 0.9382. C, for a randomly selected subject, find the probability of a bone density test score between negative 1.33 and 2.33. So, menu 552, negative 1.33, 2.33, and that's 0.8983. So the probability that negative 1.33 is less than Z is less than 2.33 is 0.8983. 0.8983. D, find Q sub 1, the bone density test score separating the bottom 25% from the top 75%. So Q sub 1 is menu 553, 0.25, and that's negative 0.67. Negative 0.67. And E, if the mean bone density test score is found for 9 randomly selected subjects, find the probability that the mean is greater than 0.5. Okay. The probability that X bar is greater than 0.5. Okay, now we're using X bar, so that's going to change this. That's going to change that. So let's go in here, menu, 553, area. Oh, the mean is greater than 0.5. That is not the one I want to use. Menu, 552, lower bound is 0.5. Upper bound is positive infinity. The mean stays 0. The standard deviation is 1 divided by the square root of 9. And that's 0.0668. 0.0668. That's 1 divided by the square root of 9, which is 1/3. All right. 2, biometric security. In designing a security system based on iris recognition, we must consider the standing eye heights of women, which are normally distributed with a mean of 59.7 inches and a standard deviation of 2.5 inches, based on anthropometric survey data from Gordon Churchill et al. So we're going to have a mean of 59.7 and a standard deviation of 2.5. All right. A, if eye recognition security system is positioned at a height that is uncomfortable for women with standing eye heights less than 54 inches, what percentage of women will find the height uncomfortable? Menu 552, lower bound negative infinity, 54. We got 59.7 for the mean, and we have 2.5 for the standard deviation. We get 0.113. So the probability that X is less than 54 is 0.0113. or 1.13%. All right, B. In positioning the eye recognition security system, we want it to be suitable for the lowest 95% of standing eye heights of women. What standing eye height of women separates the lowest 95% of standing eye heights from the highest 5%? Okay. I think I need a little thing here. I'm going to have to draw me a little. Did it again. One more time. So I want this this over here 0.95. Okay, and I'm not looking for the z this time. I want to know what the x is. Okay, so I'm going to go over here. Menu 553. Area is going to be 0.95. My mean is going to be 59.7. And my standard deviation is going to be 2.5. And I get 63.8. So this is going to be 63.8 inches. Okay. Not too shabby. Number 3. Biometric security. Standing eye heights of men are normally distributed with a mean of 64.3 and a standard deviation of 2.6. If eye recognition security system is positioned at a height that is uncomfortable for men with standing eye heights greater than 70 inches, what percentage of men will find that the height uncomfortable? So we're looking to do something like this right here. Now we're going to have our mean is going to be 64.3, and then one standard deviation to the right. We're going to add 2.6 to that, so that's 66.9, I believe, 66.9, and that would be 69.5 would be 2 standard deviations, 69.5, and we're looking for 70 inches. So we're looking right over here. That's terrible. I can fix that. Yeah, we're looking right next to that. 70 inches. What's this? What's that percentage? Well, let's see. Menu 552. We got 70 for our lower bound, positive infinity for our upper bound. We have a standard deviation of 64.3 and a standard deviation of 2.6, 0.01417. So this area here is 0.014, we'll say 142. So this is the area we're looking for, greater than. So the probability that X is greater than 70 inches is 0.0142 or 1.42%. And that's A. B. In positioning the eye recognition security system, we want it to be suitable for the tallest 98% of standing eye heights of men. What standing eye height of men separates the tallest 98% of standing eye heights from the lowest 2%? What standing eye height? Okay. So we're going to go over here. We're going to say menu 553, 0.02. And then we got a mean of 64.3, a standard deviation of 2.6, And we got 58.96. We're just going to say 59 inches. 59 inches. Number 4. Moving right along. Sampling distribution. Scores on the Gilliam Autism Rating Scale are normally distributed with a mean of 100 and a standard deviation of 15. A sample, this looks like an excellent problem for y'all to do and put on the form. Number 4. Number 5, unbiased estimators. What is an unbiased estimator? A statistic that targets the value of the population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding parameter. So 5A, an unbiased estimator a statistic that targets the value of the population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding parameter. For the following statistics, identify those that are unbiased estimators: mean, median, range, variance, and proportion. Well, the mean does. Oh, that's terrible spelling. The variance does. And the proportion does. The others do not. The standard deviation does not. And that's mostly because of the square root. Because you take the square root of it. C. Determine whether the following statement is true or false. The sample standard deviation is a biased estimator, but the bias is relatively small in large samples, so S is often used to estimate sigma. Very true. Very true. And like I said, it's mostly because you're taking the square root of the variance. 6. Disney monorail. The Mark 6 monorail used at Disney World has doors with a height of 72 inches. Heights of men are normally distributed with a mean of 68.6 and a standard deviation of 2.8. What percentage of adult men can fit through the door without bending? All right, so let's see here. It has, let's see, has a height of 72 inches. Heights of men, the mean is 68.6 and a standard deviation of 2.8. So we want to find the probability that X, X is greater than 72. Let's see, does the door, okay, what percentage of men can fit? Oh, so it's going to be less than 72. Less than 72. Does the door with the height appear to be adequate? All right, let's see. Menu 552. Lower bound is negative infinity. Upper bound is 72. Our standard deviation is 68.6. Our mean is 2.8. And that's 8.8877. 0.8877. All right. Does the door height of 72 inches appear to be adequate? I would say not for 11% of the people, not people, but men. Why? Well, because 11% of them are going to have to bend down to get in or put a knot on their noggin. 6B, it says, what doorway height would allow 99% of adult men to fit in without bending? So we're going to let y'all do 6B and then put it on the form. 7. Number 7, Disney monorail. Consider the same Mark 6 monorail described in the preceding exercise. Assuming that heights of men are normally distributed with a mean of 68.6 and a standard deviation of 2.8. Golly, all of a sudden I can't draw one. 2.8. In determining the suitability of a monorail door height, why does it make sense to consider men while women are ignored? Because women are generally a little shorter than men. A doorway height that accommodates men would also accommodate women. Women are generally shorter than men. And a doorway height B, what doorway height would allow 99% of adult men to, 7B. Mark 6 monorail cars have a capacity of 60 passengers. If a car is loaded with 60 randomly selected men, what is the probability that their height is less than 72 inches? B, all right, so the probability that X bar is less than 72. X bar. Why is it X bar? Because we have n equals 60. So that changes stuff. We're going to have to use a sigma X bar of 2.8 divided by the square root of 60. So let's try that. Menu 552, negative infinity to 72, and we still got a well, we still have a mean of 68.6, but our standard deviation changes. Now it's 2.8 divided by the square root of 60. Well, the calculator says 1, but it is actually going to be less than 1, so we're going to put 0.9999, okay? Because it is actually less than 1, but it's very, very small. C, why can't the result from Part B be used to determine how well the doorway height accommodates men? And that's because the mean height of 60 men is less than 72 inches. It does not follow that 60 individual men all have heights less than 72 inches. In determining the suitability of door height for men, the mean of 60 heights is irrelevant, but the heights of individual men are relevant. So that's because the mean is an average. All right, it is an average of 60 men. The average of 60 men is less than 72 inches. That does not mean all men are less than 72 inches. At 6 foot. We all know several people that are taller than 6 feet. Several young men, maybe even a few ladies. 8, assessing normality. Listed below are the recent salaries in millions of dollars of players of the San Antonio Spurs professional basketball team. Do these salaries appear to come from a population that has a normal distribution? Why or why not? Well, let's look. On and new document, no, and let's go to lists and spreadsheets, and we're going to put them in there. We have, I'm going to get real creative here, call it AA, and we have 12.5, 10.4, 9.3, 7, 4, 3.1, 2.0, 2.9, 2.1, 1.8, 1.4, 1.1, 1.1, and 0.9. All right. Now, let's see here. Do these salaries appear to come from? Well, what do we need to do? Let's go to on, and let's draw a graph, AA. And okay, let's turn that into a histogram. Menu, 1, 3. All right, even if we tightened it up, it's still going to go off to the right, okay, because there's a lot. So probably not. Let's go menu 1, 1 and 4 normal probability plot. Okay, I'm seeing a definite trend here, so I'm going to go with, this is A. No. The histogram was skewed to the right, and the normal quartile plot had a definite pattern that is far from a say a straight line pattern. Okay. B, that was A. What about B? Can the mean of this sample be treated as a value from a population having a normal distribution? The sample size is 13 and does not satisfy the condition of n is greater than 30, and the values do not. So we're going to say no. N equals 13, which is less than 30. Well, let's see. N equals 13 does not satisfy a condition N is greater than 30. And the values population. Let's see. No, n equals 13 does not satisfy the condition of n is greater than 30, and the values do not appear to be from a population that is normally distributed. All right. Number 9. Number 9 and 10A and B. 9 and 10A and 10B. Y'all do, and turn it in on the form. I hope all is well and everybody is safe. Y'all have a good day.